Hey everybody, it's Mr. Morris again, back for the second half of electron configuration. It's just easier to break this lecture down into two smaller videos when it comes to editing and uploading. So make sure you've already watched the first one, it was listed right above this on Moodle, and now we're ready for the second part of electron configuration. So we know that all atoms contain a nucleus at the center. They have electrons that orbit in the electron cloud. Those electrons orbit at certain distances away from the nucleus, and those distances are called shells, kind of like the layers of a gobstopper. Within each shell, there are certain orbitals or paths that electrons can follow. And the farther away from the nucleus you are, the more space there is within that shell. So the more paths we can have and the more electrons those shells can hold. Now, electrons want to fill from the least energetic to the most energetic shells. It's kind of like rooms in a building. You want to start on the ground floor and then fill the first floor, then move on to the second floor, but you have to exert more energy to walk up the steps to get there, which is why we want to start on the least energetic or the lowest energy level or shell first. So our periodic table, besides being based on atomic number, which it goes from 1 all the way up to 100 and some odd, we also are based on shells, and those shells that contain orbitals. And of course I just erased that off the screen, so we'll try that again. So shells and orbitals. There we go. So if I take my marker here and I draw a tiny little nucleus containing protons and neutrons at the center of my atom, I can then start to move outward. And so right here is my first shell. And that shell can only hold 2 electrons, and the only type of path they'll follow is an s path. I only have an s orbital within that first shell or energy level. Now as I move out, like the layers of a gobstopper, here is my second energy level or shell. And this time, because there's a little more space, there's enough room for electrons to follow an S or a P path. And I can continue on doing this. So I might draw the third energy level or shell. And again, you notice there's more space, more area for these electrons to move around in. And so now we have enough for an S, a P, and a D. And if I keep on going, notice now we're taking up a lot of space. This is our fourth energy level or shell. There's even a couple more past this. At this point, there's enough space for lots of electrons moving in lots of different directions, following lots of different paths. And I have enough space for S, P, D, and F orbitals. That's one that can hold up to 32 electrons just in that one spot. Now, obviously, all atoms don't have as many as 32 electrons. Some have less, some have more. So the ones that have less will fill the first, the second, maybe the third shell. Some will maybe just fill the first couple of shells. And the really big elements like uranium will fill the first, the second, the third, the fourth, the fifth, continuing on until we fill all the little rooms, which are the orbitals for the electrons to go, based on energy, starting with the least energetic, going to the most energetic as we move up. So moving down on the notes just a little bit. So for each element, the electron configuration is a lot like an address. It more or less tells us where. So each electron configuration is like an address. It tells the location of the element relative to the others on the periodic table. It's almost like which room on the periodic table is that element occupying based on how many electrons it has and where they go. So the full electron configuration shows every electron and its location. There's another one called the noble gas configuration, which only shows electrons after the last noble gas, and we'll talk about that here in just a second. So here is our kind of standard periodic table. Notice that, like we talked about in class the other day, the periodic table has periods, which are these guys right here that go left to right. They're the rows. And we also have groups, which are these guys right here that are vertical. Groups or families that go up and down. We don't care too much about the groups or families for today, talking about electron configuration. We care more about the periods. Okay, and the periods are kind of the address of where those electrons are going to be found. The problem is if you look down here, we don't use these guys much, the rare earth metals, the actinide and lanthanide series. And so it's almost like we just cut them out of the table so the table took up less space on the paper. Well, the problem is when we talk about electron configuration, where they are and how electrons fill those different orbitals in a certain arrangement, it does kind of matter. So what I'm going to do, and we'll give this out to you in class, is pull up a different form of the periodic table. Notice that on this periodic table, we've actually taken that bottom two rows, the rare earth metals, and we have stuck them right here where they actually go, right in line, so that now we'll use this to help figure out our electron configuration. Okay, so we know that in the first shell, we only have one s orbital, and each orbital can hold 2 electrons. That's true for any orbital we have, an s, a p, a d, an f, doesn't matter. Each individual orbital can hold up to 2 electrons. One pointing up, one pointing down. They have opposite spins, and it's kind of like being opposite in positives and negatives a little bit, but they fit in there better if one's pointing up and one's pointing down. Notice this periodic table also has helium right here and over here. That's because it could go either place. Hydrogen could just as easily get moved over here as well. They're put where they are because of electrons and valence electrons, how many they have in the outer shell. But for us, either way, works out just fine. So talking a little bit about electron configuration, we'll talk about the full electron configuration. We just start at the top left. So it's almost like a little map. Help if we have the right periodic table here. Get the mouse to work. There we go. Let's try this again. So if we start right here, and then we move from left to right, just like we read, and if we run out of space, we go to the next line, and we continue to read. Okay, so if I was going to write the electron configuration for hydrogen, I would simply say that hydrogen, the full electron configuration, is a 1 first energy level. This is an s to show that it's an s orbital within that energy level. I'm going to put a little superscript of 1 to show that there's 1 electron within that orbital, because hydrogen only has 1 electron. And I know that because it has an atomic number of 1. So this neutral atom, if it has 1 proton, also has to have 1 electron. Now, if I skip down a couple, and somehow made it blue, there we go. Let's just pick a different color here. Make this guy a little bit bigger. So let's say we want to pick right here, and we pick beryllium. So I want to write the electron configuration for beryllium. So I start right here, like I always do, on the top left, and I say that its electrons will fill the 1s orbital first. I look right here and see that beryllium has an atomic number of 4, which means it has 4 protons and 4 electrons. So those 4 electrons have to fill in a certain order, and it's always the same order as we fill. So we have 1s1, 1s2, and now we've run out of both of our 2 electrons that go in the first shell, and the first shell is full. But we're not done, so we come back to here and say, okay, the next row is a 2s orbital first, and we fill 1, 2 of those, and I finally get to beryllium, and we've used up all 4 electrons. So it always goes in the same order, 1s2, 2s2, on and on and on. So if we pick another one, this time let's pick oxygen over here on the right-hand side. Okay, well, if I'm going to write the electron configuration for oxygen, I'm always going to start in the top left, and I know that I have 8 electrons that I have to fill up. We always fill in the same order. We start up here in the top left, and it pretty much tells us what to do. So I take an s orbital in the first energy level. I can put 2 electrons there, and now that energy level, or that shell, is totally full. So I go on to the next shell, the second shell, and now I'm right here, and I say I can fit 1, 2 electrons in the second s shell, but it's full, so I continue to move across the periodic table until I get right here, and look, we have a 2p. So the next orbital we fill is the 2p orbital. And I fill 1, 2, 3, 4 electrons, and now I've used up all the electrons in oxygen. So they all have a place that they live as they fill up that electron, or excuse me, as they fill up their spots in those energy levels of those shells where the electrons like to go. So we can go on, and we can keep doing this for different elements. If we look back on the notes, there's a few more at the bottom. We already did oxygen. We could do magnesium. We could do copper. Notice that the farther down the periodic table you go, the longer it takes to write out the electron configuration, just because the more shells and orbitals we have to fill with those electrons. The other thing real quick is called the noble gas configuration. So if I look back at the periodic table, remember that everybody in group 8A, way over here on the far right, all of these guys are the noble gases. And atoms lose and gain electrons to look more like noble gases, and it has to do with being happy, being stable, and they're the most stable when there's the right number of electrons compared to protons, and they're a certain distance away from the nucleus. It has to do with forces for charges. It's called Coulomb's law. We're not going to get into that too much, but it's the idea that by having an electron configuration like a noble gas, you're more stable and you're happier, and things are good. So if I wanted to write the noble gas configuration for somebody like magnesium, then instead of having to write 1s2, 2s2, 2p6, on, I can say, okay, here's magnesium in row 3. I find the noble gas right before it in row 2, which is neon. I put that in brackets to show that's where we're going to start, and I simply go from there. So now all I have to do is write neon, and then the next shell and orbital we run into is a 3s, and I fill up both of those spots, and now we're finished. So instead of having to write 1s2, 2s2, 2p6, 3s2, by doing it this way, this is called the noble gas configuration, it just takes up less space. It always goes in the same order. Electrons always fill from 1s1 first. We always put 2 in each orbital before we kind of move on to the next. There are a few weird exceptions towards the bottom of the periodic table that we'll talk about more later. But for now, it's just more or less a little bit of practice of saying, okay, here's this order that it always goes in. 1s2, 2s2, 2p6, 3s2, 3p6, and it all has to do with energy and where electrons go. And that's all we have to do for electron configuration. It's just one way to show where the electrons are, how they orbit the nucleus, how many electrons an atom has, and how much energy those electrons have, depending on where they're at. So we'll talk a lot more about this in class as we go. This is just kind of the beginnings to give you some information, and we'll definitely talk more as we get this figured out.